Good morning, teachers and fellow Assumptionites. My name is Kylie, and here with me is Jaden, and we are both from Class 3 Manual. Today, we'll be presenting to you our presentation on earthquake-proof buildings.
You may be asking, what is an earthquake? An earthquake is the sudden release of strain energy in the Earth's crust, resulting in waves of shaking that radiate outwards from the earthquake source. When stresses in the crust exceed the strength of the rock, it breaks along lines of weakness, either a pre-existing or new fault plane. What are the impacts that earthquakes have on structures?
Earthquakes can result in the ground shaking, soil liquefaction, landslides, fissures, avalanches, fires, and tsunamis. The extent of destruction and harm caused by an earthquake depends on magnitude, intensity, and duration. What are some methods that engineers around the world use to design and construct earthquake-proof buildings?
There are four different methods to constructing earthquake-proof buildings. Firstly, they can create a flexible foundation. Secondly, countering forces with damping. Thirdly, shield buildings from vibrations. And lastly, reinforcing the building structure.
How do engineers carry out these processes? One way to resist ground forces is to lift the building's foundation above the earth through a method called base isolation. Base isolation involves constructing a building on top of flexible steel, rubber, and lead pads. When the base moves during an earthquake, the isolators vibrate while the structure remains steady. This effectively helps to absorb seismic waves and prevents them from traveling through the building.
Next, if you're familiar with shock absorbers used in cars, you might be surprised to learn that engineers also use a version of them in earthquake-resistant buildings. Similar to their use in cars, shock absorbers reduces the shock wave's magnitude and help reduce pressure on the building. They accomplish this in two ways: vibrational control devices and pendulum power. Vibrational controlling devices involves placing dampers at each level of a building between columns and beams. Each damper consists of piston heads inside a cylinder filled with silicon oil. When an earthquake occurs, the building transfers the vibrational energy into the pistons, which push against the oil. The energy is then transformed into heat, dissipating the force of the vibrations.
Pendulum power is another common damping method which is used primarily in skyscrapers. To implement this, engineers suspend a large ball from steel cables that connect to a hydraulic system at the top of the building. When the building begins to sway, the ball acts as a pendulum and moves in the opposite direction to stabilize the building. Like damping, these features are tuned to match and counteract the building's movements in the event of an earthquake. Rather than just counteracting forces, researchers are experimenting with ways buildings can deflect and reroute the energy from earthquakes altogether. Dubbed the seismic invisibility cloak, this innovation involves creating a cloak of 100 concentric plastic and concrete rings and burying it at least 3 feet beneath the foundation of the building. As seismic waves enter the rings, ease of travel forces them to move through the outer rings. As a result, they are essentially channeled away from the building and dissipated into the ground.
To withstand collapse, buildings must redistribute forces that travel through them during a seismic event. The four centrals to reinforcing a building are shearing walls, cross braces, diaphragms, and moment-resisting frames.
Shear walls are a useful building technology that can help transfer earthquake forces. Made of multiple panels, these walls help a building keep its shape during movement. They are often supported by diagonal cross braces made of steel. These beams can support compression and tension, helping to counteract pressure and push forces.
Cross braces attach to a building's frame by bracing stud to stud in an X pattern to increase load capacity. The use of cross bracing keeps buildings stable against high winds and seismic activity. Diaphragms are also a central part of a building structure, consisting of the building's floors, roof, and the decks placed over them. Diaphragms help remove tension from the floor and push forces to the building's vertical structures.
Moment resisting frames provide additional flexibility in a building's design. These structures are placed among a building's joints and allow columns and beams to bend while the joints remain rigid, so that the building can resist the larger forces of an earthquake while still allowing designers the freedom to arrange building elements. While shock absorbers, pendulums, and invisibility cloaks may help dispel the energy to an extent, The materials chosen for a building are equally responsible for its stability. These materials include structural steel, wood, and futuristic materials.
What is the safest type of building for an earthquake? A taller structure is much safer than a stiffer and shorter building. Flexibility is essential during the shaking associated with an earthquake, and often, the taller the building, the more flexible it is. In fact, engineers must design shorter buildings in earthquake-prone areas to withstand even greater forces than those of a taller building.
Of course, it is important to account for the materials that are used in the building to determine how well it can withstand earthquakes. Timber, steel, and reinforced concrete are the most popular materials used to construct earthquake-proof buildings.
One earthquake-resistant material that is suitable for withstanding the impact of an earthquake is structural steel and timber.
For a material to resist stress and vibration, it must have high ductility, which is the ability to undergo large deformations and tension. Modern buildings are often constructed with structural steel, which is a component that comes in a variety of shapes and allows buildings to bend without breaking. Timber is also a surprisingly ductile material due to its high strength relative to its lightweight structure.
Thank you for listening to our presentation.